So last time we talked about scientific notation and numbers that are quantitative measurements, and we also talked about qualitative measurements. So today we're going to talk about accuracy versus precision, show you how to calculate percent error, and then show you how to measure things. And I know you're like, I know how to measure things, but we're going to show you a little bit better technique. So accuracy is how close a measurement is to the true value of what is being measured. Precision is how close multiple measurements are to each other. So the key is to know precision. If you know what poly means, it means many. Precision is how close a series or many measurements are, how close they are together. So precision, poly, many. It's a series of measurements and how close they are to each other. Accuracy is just like you think. It's how close to the true value. So let's say on a dartboard, you shoot right in the middle. We would say that that's an accurate shot. But let's say that you shoot mini darts, and they all go right in the middle. Then not only are your shots accurate, but they're also precise. Let's say that you shoot mini darts on the bottom here. We would say that these are precise, but if you were trying to get the bullseye, this would not be accurate. But if you know darts and you were playing crickets, maybe getting that down there, it might be the one that you need. So, if we take a look here, if a block weighs exactly 101 grams, scientists measured this with everything in the world they could, and they found out it's exactly 101 grams. This is just an ideal situation. Student tries for 3 times to measure it. He gets 101.0, 107.5, and 101.1. Well, out of these, this is the most accurate one. This one is way far away, so that's probably an outlier. The student should probably throw that out. And then they have these 2 measurements, which are both precise, because they're close to each other. To find out how off you are of something, if you know the actual amount, you would calculate what's known as the error. So if we did this, we would have 0 for the error. If we did this, we would have 0.1 grams for the error. And if we did this, we would have 6.4 grams for the error. And to find that, all I did was take the actual, which is the 101, minus the experimental error, minus the experimental. This error right here shouldn't be there. Hopefully I'll have that deleted on the final version. Actual minus experimental. So, in reality, this would be negative 6.4 and negative 0.1 grams, because this does hold a positive or negative value. You could be positive above the reality or above the actual, or you could be below it. Every instrument that you use has some form of error. If you've ever seen meter sticks in a classroom, you know that kids are beating those things against anything they can, as well as there's probably some manufacturing error as well. So, let's take a look at what we do with error. So we can also find the percent of error that you have. And this would be like if you got an 85% on a test, and you would have 15% error on that test because you missed 15% of the problems. So to do this, we notice we take the error that we got from before. Notice these little lines. That means we get rid of that value because the percent's always going to be positive. So if it was negative, it becomes positive. If it's positive, it's still positive. And we take that error and we divide it by the actual value. So let's try one of these. Working in the lab, a student finds the density of a piece of pure aluminum to be 2.85 grams per centimeter cubed. The accepted value for the density of aluminium is 2.699 grams per centimeter cubed. And if this part's messing with you, don't worry about that right now. We'll get to that. What is the student's percent error? So the accepted value is the true value. So I'm going to go ahead and set up my percent error over here. The actual or accepted value is going on bottom. Now we've got to find the error. So we need to take 2.699 and subtract 2.85. Both of these are in grams per centimeter cubed, so our final answer is going to be grams per centimeter cubed. So I'm going to go ahead and type that in. 2.699 minus 2.85. And my calculator is still in scientific notation. If that bothers you, you can switch to normal for most of the stuff we're doing at the beginning, but you're going to get used to scientific notation, hopefully, as we progress. So that is negative 0.151 grams per centimeter cubed. So I'm going to put that at the top, and since I have these absolute values on there, that's going to basically get rid of that negative and make it a positive. And then, as any time you want to make a percent, we have to multiply by 100. So I've got this. I'm going to go ahead and get a negative answer. Actually, I'll type it in since you guys are just getting started. So I type in the 0.151. I divide it by 2.699. I get that, but that's not my percent until I multiply that by 100. Boom. We always take percents out 2 decimal places. So this is 5.59% error. Now, if you got a 93 point something on a test, or 94 point something on a test, you'd probably be pretty happy. This is only 5.59% off. If this were some medical procedure and it was 5.59% off, that might be bad. You might not want that. So for homework tonight, you should finish problems 2 and 3. Let's take a look then at how to read scales. Reading scales. When measuring, it is important to make sure you write down all of the known numbers and one estimated digit. This is the one that everybody forgets. I'll show you why it's important here. We know this is between 800 and 850, so we know that the hundreds place is 8. If this is 850, that makes this 810, 820, 830, 840, 850. That means that this is 810, this is 820, and this is 830. That tells us that the second, or the tens place, is 2, because it's between 820 and 830. Now, if somebody owed you $820 some dollars, would you be okay with 820? Or if you owed or if somebody owed you 820 some dollars, would you be okay with 820? You would probably want to know exactly how much. So we go and we divide this thing basically into tens. So that makes this right here, even though there's not a dot there, that makes that 821, 822, 823, 824. And I think I'm going to go with 825 here. I think that's almost right in the middle. If you want to zoom in or get out your magnifying glass, you're more than welcome to. I'm going to go with 825 for that. Let's try another one. Let's try this one, because this one's interesting. 79 and 78. It's between 79 and 78, so that means it is 78. It's always the lower number, even if it's written opposite way. So that's 78 point. That's 78.1, 0.2, 0.3, 0.4. It's between 0.4 and 0.5, so it's the lower of the two. 78.4. I think that that's a little bit more than halfway, so I would be happy with 78.46, or I might even go all the way to say it's 78.47. Now keep in mind, that's why this is estimated. I might read that a little bit different than you. The other thing you have to keep in mind is most of our instruments that we measure with, we can move on ourselves, like a meter stick or something like that. You actually control where it is. So you need to make sure that you line up your ends perfectly. That way you get a good estimation there. One more. Let's do C. So here's 0.3 and here's 0.4. So 0.3. This is a little bit different because this is 0.32, 0.34, 0.36, 0.38, 0.40. So we need to make sure that we're careful here. So there is a marking for 0.32, 0.34. And I'm going to say that's real close to 0.35. So I'm going to go 0.349. And you can notice that this arrow is a little bit up, and that's just a problem with Google Docs. But that's going to help you guys for this, because look where this one is. It's between 15 and 20. So 15. So if we look here, we're at 15. This is 20, 16, 17, 18, 19, 20. So 15, 16, 17. Now, it looks to me like that is right on the 17, but I haven't estimated anything if that's right on the 17. So that means that I have to estimate one digit. What are their lines for every single one? 15, 16, 17. So I have to go out one more decimal place, and if it's right on that 17, then I'm going to put a 0 there, because I know it's not a little bit closer to 17.1 or a little bit before. Otherwise I wouldn't have put 17, I would have put 16.9. But it's right on there, so that's 17.0. Excellent. If you would also finish the rest of this for homework, or if you have time in class, that's good too. And that is basically our first unit. That completes our first unit. Our first unit test, though, is actually 3 units. We have combined unit tests.